Hello everyone, welcome you all at Lokesh Sir Unlimited Study Zone, and we're starting here the chapter number 4. This is very important chapter and one of the big chapter of our 12th class series, moving charges and magnetism. So first, let us see the syllabus prescribed by CBSE for this year 2025 and 26. So unit number 3, chapter number name magnetic effect of current and magnetism. Okay, so chapter will be in two part. Uh, According to the unit, first we have to cover in this segment is magnetic effect of current. Okay, so the theme of the chapter is magnetic effect of current. So in this chapter, we are totally look the concept of magnetic effect of current. Magnetic effect of current. The unit name is moving charge and magnetism, but the name of the chapter is magnetic effect of current. Okay. Yes. So moving charge and magnetism. In the magnetic effect of current, we have to deal with the total chapter in two parts. First, there is the effect of a moving charge, and there second is the um effect of magnetism. Okay, so there are two parts in this chapter. First, we have to cover the effect of moving charge, and second part is magnetism. Now, come to the topics of the chapter. First, it is concept of magnetic field and Oersted experiment. So let us see. We start with the concept of magnetic field. Concept of magnetic field. First topic. Okay. So question is, what is magnetic field? So magnetic field, it is the invisible field around any magnet. Two things are there. Around any magnet, north-south magnet is there. The invisible field around any magnet, or second is magnetic dipole. Like this is a current carrying conductor, behaves like a magnetic dipole. The upper one pole will be south here, sorry, as the clockwise current is here, and the below one will be north. So magnetic dipole here and current carrying conductor also. These are the sources of magnetic field. Okay. So the reason up to where I can realize the magnetic force is called magnetic field. Oersted is the first scientist who discovered the magnetic effect of current. The motto of this chapter is to experience the magnetic effect of current. Magnetic effect of current. Before Oersted experiment, everyone depends on the magnetic effect because of only magnet. No one knows that a current can also produce a magnetic effect. Okay, no one knows. No one knows this fact that a current can also produce a magnetic effect. People understand that only magnet can produce magnetic effect, means magnet can attract the magnetic material towards itself. Like here it is a magnet given bar magnet, and this is some magnetic material. So it can be attracted only by this magnet. Okay, this is when before Oersted experiment. Now, when Oersted forms his experiment, when in year 1820, yes, 1820 means just at the beginning of 19th century. So 1820, in year 1820, Oersted performed his very famous experiment. Maybe you have studied about this in class 10th. What Oersted done? He taken a current carrying conductor. That time only DC current is possible. So he taken a current carrying conductor. Okay. And by a cardboard, he placed this current carrying conductor. just passing through the center of the cardboard. Clear, beta? Now, he provided the connection. Yes, a rehosted is there to increase the amount of current. Okay, tap key is there to on and off the switch, and battery is there, plus minus. So he makes such a connection like this, and when he on the switch of the battery, the current will flow. What happened? He sprinkled the iron fillings over this board. Yes, iron fillings. I can take here this color. So he spread the iron fillings. First, he distributed the iron fillings all over the board and flow the current. Now he tap this board, tuck, 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 like this. He see that iron fillings are arranged in the form of concentric circles. Clear, beta? He saw that the iron fillings arrange themselves in the form of concentric circle. Means there is a invisible power, okay, that can arrange these particles in the form of concentric circle. These lines of forces, those are in the form of concentric circles, are magnetic lines of forces. Okay, so these magnetic lines of forces arrange the iron particle, as iron is a ferromagnetic substance. So they arrange the iron particle just upon them. So in this way, there is the discovery of magnetic field due to current. Yes. So here is the clear production of magnetic field taken place with the help of only current, with the help of current. That's why this topic is called magnetic effect of current. Okay, of current. Now, magnetic field is developed. Another question is in mind of Oersted, that in on what factor this magnetic field depends. So Oersted performed few more experiment in the same arrangement, in the same setup. So first thing, Oersted has increases the amount of current, increases the amount of current, and he taken a magnetic needle too. Yes, he taken a magnetic needle too near this current carrying coil. So suppose this is the magnetic needle. Okay. Yes. So this is the north pole of magnetic field. I colored it with red color. So this one is north and this one is south. So what is happening here? When Oersted increasing the amount of current, the deviation of magnetic needle, or you can say magnetic needle rotated more and more, it means the amount of magnetic field is directly proportional to the current flowing through the conductor. So first result is B is proportional to I. As you increases the amount of current, the magnetic field will also increasing. Okay, increases. Clear? So on increasing the magnetic amount of current, magnetic field is also increases. Second experiment, as Oersted taken this magnetic field far away from the current carrying conductor, the needle in the the deflection in the needle decreases slowly, slowly. Okay, as you go away from this coil, sorry, this is not a coil, this is a straight conductor. The magnetic field is continuously decreasing. It means Oersted observe that B is inversely proportional to R. Okay, he is not clear about what is the power of R, but there should be some power of R as it is decreasing with respect to radius. Okay, third, third result is once Oersted change the direction of current, like here the current is going from positive to negative. Okay, as battery polarity of the battery, plus is here and minus is here, so current is going in upward direction. So when Oersted change the direction of current, means he opposite the polarity here. If we taken here minus and here it is plus, so just the direction of the current becomes change. Then what happened? The direction of the magnetic field also reversed. Yes, this means the orientation of pole is totally reversed. North pole will pointing outside and south pole will pointing inside. Clear? So what is the observation on reversing the direction of current? On reversing the direction of current, magnetic field, the direction of magnetic field, sorry, the direction of magnetic field also reversed, also reversed. So these are the three results obtained by Oersted experiment. So on this basis, Oersted had established his famous experiment 1820 on year 1820 and discover about magnetic effect of current. Yes, let us see. So in introduction, in the year 1820, Oersted realized that electricity and magnetism was intimately related. So here you can see there is a clear some sort of relation between electricity and magnetism. Okay. So you have seen here ki with the help if input of electricity means if you have current, then result is what? B. Means magnetism. Okay. So there is the development of magnetic field because of electric current. Okay, this was proven by Oersted. After then, after 30 to 40 years, a scientist was there is Michael Faraday. He produced current with the help of magnetism. Okay, first Oersted was there. He developed magnetic field with the help of current. Then after Michael Faraday is there, he develops. Here is the development of magnetism, and here is the development of electricity. Okay, electricity by magnetism. Clear? So you can say there is the strong relation between current and magnetism. Yes or no? This whole subject under which you study the relation of electricity and magnetism is called electromagnetism. Electromagnetism. Okay. And you can see there is an interrelation between electricity and magnetism. There is a production of electricity with the help of magnetism. This is called electromagnetic induction. This is called electromagnetic induction. So the first part of the chapter, development of magnetic field with the help of current, is comes under the chapter magnetic effect of current. So when you develop with the help of I, if you're going to develop magnetic field, then this the name of this chapter becomes magnetic effect of current. Clear? Of current. So the whole phenomenon related to the production of magnetic field comes under the topic magnetic effect of current. But when you having magnetic field and you develop electric current, then all the theories and concepts related to this segment comes under the topic electromagnetic induction. Understood? Induction. So you see here, in the year 1820, Oersted realized this thing. Yeah. Oersted realized this thing that electricity and magnetism were intimately related. Yes, there is a very strong bonding between electricity and magnetism. He shows that electric current through a straight wire cause noticeable deflection in the magnetic compass needle near the wire. We just have performed this experiment. We keep a magnetic needle there, and you have seen there is a deflection. Yes or no? So magnetic compass needle held nearer the wire. He also found that the magnetic field needle aligned tangentially to an imaginary circle which has the straight current carrying wire as its center and its plane perpendicular to the wire. Yes, what is the observation? See here, like The direction of wire is perpendicular to the plane of paper. Like this is the plane of paper, and here it is the wire. Here it is the wire that is penetrating the plane of the paper. Understood? Now this is the magnetic field. You see the plane of magnetic field is just perpendicular to the direction of current. Yes or no? This is the plane of magnetic field. So magnetic field produces in this plane, xy plane. If you consider this axis as x, considering this axis as y, so the magnetic field produces in xy plane and current is going on z axis towards z axis. Yes or no? So this means current is always perpendicular to the plane of magnetic field. Yes. There is B is always perpendicular to the I. Clear? So note it down. Magnetic field always produced in the plane perpendicular to the electric current. Okay? Perpendicular plane produce in the plane perpendicular to electric current. Electric current. Clear? Yes. So this is the observation of Oersted. Here you can see this is the direction of current. Yes, current is coming outward, dot representing the outward current and cross representing the downward current. So two things are there. Outward current in the experiment, I told you Oersted changed the direction. First, it was the current is coming out of the paper, and second, the current is going downward the paper. Yes or no? So two results are there. Yes, when current is coming outward the paper, so if this is north and this was south, and after changing the direction of current, this become north and this becomes south. So you can clearly observe here there is a change of direction of magnetic field. Yes or no? On reversing the direction of current, right? Yes or no? Okay. So and this is the pattern of magnetic lines of forces. So we have taken idea here that with respect to a current carrying conductor, the pattern of magnetic field is a concentric circle. So write it. With respect to a current carrying conductor, straight conductor. Okay. With respect to a straight current carrying conductor, the magnetic field is in the form of concentric circles. Clear? Concentric circles. Okay, later on we will derive a relation for the magnetic field due to a current carrying conductor. Okay, at some distance r. So you will see there is also a geometry of concentric circle will takes place by mathematical derivations. Okay. So he also found that the magnetic needle is aligned tangentially to an imaginary circle which has the straight current carrying wire as its center and it has a plane perpendicular to the wire. So make it this one underline. Has its plane perpendicular to the wire. Yes. I'm emphasizing this line because this is very important. Yes. If the direction of the current in the wire is reversed, the direction of the deflection of the magnetic needle is also reversed. Yes. When you change the direction of current, the direction of magnetic field also reverse. The deflection increases on increasing the current of the wire, bringing the magnetic compass needle more closer to the wire. Yes, if you are more closer to the wire, the deflection will increases. Okay. So if R is decreases, if you're decreasing the R, then the magnetic deflection will be increases. It means magnetic field will be increases. Okay. He also found that the iron fillings is sprinkled around the wire and arrange themselves in the form of concentric circle with the wire as the center in the plane perpendicular to the wire. Here is the practical demonstration. Look here. So previously the North Pole was here. The North Pole was here. Okay. As you deflect, initially, try to understand. Yes. Initially, the needle was in this direction. Yes. This dotted line represents the initial state of the needle before flowing the current. Yes. When the circuit is off, then needle in this direction. Clear, beta? When the switch is off, the needle is in this direction. Yes. This one is the north pole and this one is the south pole. As you switch on the current, the direction of the needle will be like this. There is some magnetic field developed. So needle will be change its direction. Okay. From the red one to the blue one. Clear, beta? So clearly you can observe here the north pole moving towards here. Okay. Now current is going from positive to negative. So current is like this, entering from bottom to top direction. Okay. Or down to up. Now if you change the direction of current, now here plus pole is there. So the current will be here. Previously the north pole moved towards the left of the center line. Here the north pole will move toward to the right of the center line. Clear or not clear? So what is concept here? The concept incorporated is if you change the direction of current, then the direction of needle also get reversed. Clear? Yes. So once again, see second paragraph. He also found that the magnetic needle is aligned tangentially. Yes. You can draw the magnetic lines of forces by taking a magnetic needle. Like in schools, you can perform this experiment like this. You take a current carrying conductor here. Okay. And take a magnetic needle here. Okay. So when you place a magnetic needle here at same in class 10th experiment, there is a tangential. Yes. This like north, south, north, south, north, south. So when you draw the pattern of magnetic field using a magnetic needle, so always this like pattern can be traced. Okay, using a magnetic needle. Same thing is here. He also found that the magnetic needle is aligned tangentially. Yes, this is the direction of tangent. Here this is the direction of tangent. If you take in randomly any one circle, then aligned tangentially. Yes, like this. Who aligned tangentially? The magnetic needle was aligned tangentially. Clear? And all needle when aligned tangentially and you join all the point, then you will have a circle. Yes or no? Like in class 10th, when you draw the pattern of the magnetic lines of forces, first you have taken a needle and you plot the direction of the north pole. So first your north pole is here, then second is here, then third is here. Then after you join all the north pole and you have the magnetic lines of forces. Clear or not clear? Similarly, you have to do here. You have to plot all the north pole. Then you will have a concentric circle. So thing was told here. He was found that the magnetic needle is aligned tangentially to an imaginary circle. Yes, these magnetic needles are aligned and form a circle. Form a circle. What does it mean? It means that the round lines of forces, or you can say the unit north pole moving on a circle. And what is magnetic field? Magnetic field is the path upon which a unit north pole can move. So this is the trace out upon which a unit north pole can move. So this is the magnetic lines of force. Clear? Okay. So imaginary circle which has the straight current carrying wire as its center. Yes, like this is the center and these are the magnetic lines of forces. Okay. So magnetic lines of forces in the perpendicular to the plane of wire. Wire is going upward and magnetic lines of forces is in the plane of paper. Understood? Any problem now? So guys, this was our first topic, concept of magnetic field and Oersted experiment completed. Hmm. Magnetic field. The magnetic field is a space around the conductor carrying current. So now previously it was in the magnetism. Magnetic field is a space around a magnet. But this definition is not completely correct here because we know the magnetic field is also developed around the current carrying conductor. So magnetic field is a space around the conductor carrying current, or you can say current carrying conductor, or the space around a magnet in which its magnetic effect can be felt. Okay, in which its magnetic effect can be felt. Okay, so the space up to where you can realize its magnetic effect is called magnetic field. Magnetic field is a vector quantity and it is denoted by B. Actually, B represent strength of magnetic field. Yes, it is about strength of magnetic field. Clear, beta? Yes, so note it down. The quantity related to the magnetic field is B vector that represents the strength of magnetic field. Like same in the electricity, like there is a charge. So charge have its own territory up to which it can exert a force. So up to certain point, the presence of electric field is given by electric field intensity. So likewise, if there is a magnetic power or there is a magnetism surrounding a current carrying conductor or surrounding a magnet, so up to a particular point, the strength of this magnetism is given by B vector at this point. And B vector means the strength of magnetic field, okay, or intensity of magnetic field. So E vector means strength or right. E vector equals to, it's a vector quantity. E vector is equals to strength oblique intensity, intensity of electric field, and B vector is said to be strength or intensity of magnetic field. Clear? Field. Some another name was also there of B, varying accordingly to the chapter. Here it will be only intensity of magnetic field, but in electromagnetic uh, electromagnetic theory, electromagnetic induction, B is called phi upon A. This is called magnetic flux density. Magnetic flux density. Clear? Yes, B equals to magnetic flux density. Similarly, here E is equals to phi electric per unit area. That is equals to electric flux density. Here it is called electric flux density. Electric flux density. Yes, and here it is magnetic flux density. Clear? Okay. Next, our next concept is Biot-Savart law and its application to the current carrying loop. Yes, so we are going now that as I said that there is two part of this chapter. First is the study of charge behavior in a magnetic field, and second is the production of magnetic field due to a current carrying coil and a different type of current carrying loops. So first we are going with the production of magnetic field with a different type of current carrying loops. Okay. So dear student, first we are going to develop all the relations, develop all the formulas uh, for the magnetic field. As we know till now that there is a production of magnetic field due to a current carrying coil. Yes, if you flowing a current in any of the current carrying wire, it may be coil, it may be rectangular loop, whatsoever it is, there is a production of some magnetic field in the surrounding area. But we want to know here that how much amount of magnetism is produced. How much amount of magnetism is produced. So a general law, a general law to evaluate the amount of magnetic field strength near a current element or near a current carrying conductor. So consider it a current element. Why? When there is a wire of to infinite length, and if you consider this length of this very small element is dl carrying the current I, then this element that having the current element I is called current element. Okay, current element. Yes. So the current element, this current element is different from the current element of here. Yes, see here. Why? In this one current element, the direction of current here is the directly upward direction. But when the current came here, when the current will come here, then the direction of current will be same, but the direction of the current will be changed. Okay. So this is a different current element, and this supposed to be a different type of current element. Okay. Two type of current elements. So a long wire can have infinite current elements. A long infinite wire can have infinite current element. Okay. So first we are going with magnetic field due to a current element. Yes, by its Savart law. So first you are going to find the magnetic field due to a current element. Why? Because of current element. Like this is a conductor, and we have taken a current element very small differential length dl with direction of current is d, and we will going to find the magnetic field at a distance r. Like this is the distance r, and we go to find the magnetic field intensity at point B. As this length is very small with the name dl, so we will calculate the very small intensity called dB, right? Because of this very small length, supposed to be differential length, the name of this length said to be differential length. This differential length, due to this differential length, the magnetic field at this point is equals to dB. Okay. Now there are this wire is supposed to be combination of a numerous number of DLs are there. Yes or no? So what is the technique to calculate the all the magnetic field from dB to B? How you can get dB to B? Just integrate dB. Okay. So when there is a continuous variation or continuous distribution because of some element, and you have to find the total value, then you need to integrate the differential value or a small value over a period or over a length. Okay. And you will get the total magnetic field intensity. Okay. Yes. So this is the concept behind this Biot-Savart law. Now, magnetic field due to a current element, it is given by Biot-Savart law. Biot and Savart are the two scientists, two physicists, those who have given the concept to find the magnetic field because of a current element. Okay, if there is a current element and up to sub distance r, you have to find this magnetic field. What is dB? So this beautiful formula is given by Biot and Savart. Yes. Biot-Savart law is an experimental law predicted by the Biot and Savart. This law shows the relation between the current in a conductor and the magnetic field it produces. Yes. So what we are going to do, according to this law, we are going to show the relation between the current in the conductor. Okay. We have a conductor in which some current is flowing, and we are going to derive the amount of magnetic field because of it. Okay. It produces. So let us consider a very small current element, a small element of length dl of a conductor xy. So here it is a total conductor of varying length, varying direction, x and y. So here it is a random conductor, any random conductor you have. Yes. So this random conductor may have infinite current element. If you divide this conductor in very short dl element, there may be infinite dl element, right? But out of them, you have to suppose only one length element. Yes. So let us consider a small element of length dl for conductor xy carrying a current I. Okay. So when you merge current I, when you merge current I with the length dl, this become current element. Okay. Current itself is a scalar quantity. Remember, current itself is a scalar quantity. Okay. Current is a scalar quantity. But dl is a vector quantity, and the direction of dl vector is considered in the direction of current. And when current mix with this length element, then it becomes idl. So idl is a vector quantity, and it is called current element. Okay. Yes. Separately, current is called I. DL is only called differential length, or incremental length is small length. Okay. And when you mix the I with dl, this whole quantity become ideal. And ideal itself is a vector quantity. And the direction of ideal means current element is what? In the direction of current flowing. Okay. In the direction of current. So the direction of ideal or current element is in the direction of current. So let us consider a small element of length dl. Previously it was length dl. Of a conductor xy, current I. Let R be the position vector of the point P from the current element ideal, and theta be the angle between dl and R. Yes. Now see, we have this one as a complete length. This is x, this part is x, this part is y. Out of that, I have considered a very small length of dl that is also flowing a current I. Here, same current is flowing through it, and we have to find the intensity at this point. Consider this is the point P, which is at the distance r from the current element. Okay. So itself a vector that joining the center of this current element to this point is called R vector, right? So this complete vector is all vector. Okay. And there is an angle between current element and R vector. Yes. See here. This is the angle between current element and R vector. Where? This one. This is called theta. Clear? Now, Biot-Savart law, according to his experiment, he suggested some postulates, or you said to be some rules to find the intensity of magnetic field. But before that, read here. Let R vector be the position vector of the point P. Yes, from the current element. So as I drawn here. What is r vector? R vector is the position vector of point P from where? From the current element, current element. Okay, from the current element, ideal, and theta is the angle between dl vector and r vector. Remember, so two vectors are there. Theta is the vector between ideal vector and r vector. So this whole become ideal vector, and this position vector become r vector. So theta is the angle, right, beta? So all the things we have now according now direction of magnetic field. So stretch your right hand thumb. Okay, stretch your right hand thumb and align your right hand thumb along this dl vector. Yes, dl vector. This is your thumb, right hand. Remember, right hand thumb, and you align your dl vector. So your fingers must be here. Yes or no? Clear or not clear? Now just fold the fingers surrounding the current conductor. Okay? Yes or no? You see towards the area of your wrist part, where your wrist is there, all the fingers are moving inside. Yes or no? In the same way, the magnetic field will comes and penetrate the diagram, penetrate your plane inside to the plane, penetrating the lines of forces inside to the plane of paper, right? So here the magnetic field will be inward, and inward magnetic field is said to be cross field. Clear? But if you considering your point here, you understand the lines of forces, your fingers are curling outward. So the magnetic fields will be outward here. Understood? So all the position to the right hand side, or you can say towards your wrist, the magnetic lines of forces will be penetrate inside the paper. So the magnetic field will be inside, perpendicular into the plane. Yes or no? And here, everywhere toward the left of the conductor, direction of magnetic field will be out of the plane. Understood? One more time. See, here it is a current carrying conductor, right? Now place your thumb here. Place your thumb here along the current carrying conductor. Now you see your remaining fingers are curling like that inside. Okay. Now observe the pattern of magnetic field here. Here penetrating, then backside, and here coming outward of the plane of paper. Understood? Again here, more lines at this point. And here outward, and again this point downward. Clear or not clear? Yes. So magnetic field direction completed. Now, the current element ideal is a vector. Its direction is the tangent to the element and acting in the direction of current flow. Yes, what I have said, the same thing is here. Ideal is the current element, and current element is a vector quantity. And what is the direction of current element? It is strictly in the direction of current flow. Okay. So ideal here is the direction of current flow. Now I'm changing my pen color. Now this is the direction of ideal, and this is the point here, and you can say the field is propagated perpendicularly into the plane of paper. That's why it is cross field. Clear? And this is the point P, and the distance up to which we have to calculate the magnetic field intensity is vector r. This complete vector is vector r. Okay. Now, according to the Biot-Savart law, magnetic field dB vector is called magnetic flux density. Yes, the other name of magnetic field, I just told you it is called magnetic flux density. Yes or no? Same it is magnetic field intensity, same it is magnetic field strength, same it is magnetic field density. Okay. All name refers to one quantity, that is B, magnetic field intensity. According to the Biot-Savart law, the magnitude of the magnetic field intensity dB called magnetic flux density at a point P due to the current depends upon the following factor. Yes, this is the main law. First, according to his experiment, first dB is proportional to the current flowing through the conductor, right? As Oersted said, as you're increasing the amount of current, the magnetic field is also increases, right? Second, dB is proportional to dl. Okay, the magnetic field is directly proportional to length of the conductor. More will be the length of the conductor, more will be the magnetic field, and dB is inversely proportional to r square. Clear, beta? And dB is proportional to sine of theta. Clear? dB is proportional to sine theta. So these four fundamental important observations are given by both scientists, Biot and Seward. I am writing here. First, dB is proportional to I, the current in the conductor or current in the current element. Magnetic field intensity is directly proportional to the current in the current element. Second, dV is proportional to dl. Second observation. dV is inversely proportional to r square inversely proportional to the square of the length, right? Third, and dV is inversely proportional to sine of theta. Fourth, now merge them all by 1, 2, 3, 4. 1, 2, 3, and 4. If you merge them all, you will get dB is proportional to I dl sine theta divided by r square, right? So dB equals to proportionality sign. Eliminate the proportionality line sign. Same in the electrostatics, you getting a constant k that is equals to 1 by 4 pi epsilon naught. Here the value of constant is always mu naught upon 4 pi. Okay, and I dl sine theta by r square. Okay, so this is amount of magnetic field due to the differential length, due to the elemental length. Okay, so dl is what? Dl is very small length and it is called elemental length. It is elemental length. Clear? It is called elemental length. So dv is equals to mu naught upon 4 pi I dl sine theta by r square. Clear? So dB is proportional to ideal sine theta by r square. Now, eliminating the proportionality sign, there is a constant. dB is equals to k ideal sine theta by r square. Here k is a constant whose value depends on the system of unit. What unit as you are choosing, whether you are choosing SI unit or CGS unit. Okay, for different type of unit, there is different value of k. Okay, chosen for the measurement of the various quantities and also on the medium between the point P and the current element. It also depends on the medium between the point and that current element, like what intervening medium you are taking here. Like if there, here it is a air between the two current element and this point P, then there will be mu becomes mu naught. For air, it is mu naught. Clear? Hello. But if there is some another medium like water is there, then for mu, it should be mu water. Clear? Yes. So for air, it is equals to mu naught. When there is a free space between the current element, when there is a free space between the current element, then the value of current k is equals to constant k equals to mu naught upon 4 pi. Clear, beta? And the value of mu naught upon 4 pi equals to 10 to the power minus 7 in SI unit. Okay, the magnitude of k equal to 10 power minus 7 and the value of k equals to 1 for CGS system. Clear? So for SI unit, dB equals to mu naught upon 4 pi ideal sine theta upon r square. We just have placed here the value of k as mu naught upon 4 pi. Clear? And for SI system, you have to place the value of k here equal to 1. So it will become ideal sine theta upon r square. Okay. So for objective question, it may be questioned that what is the value of magnetic field intensity dB due to elemental length for in CGS system. Okay. So for CJ system, k equal to 1. Clear? Clear, bachon? Okay. Now in vector form, this is also very important. Vector form, because the magnetic field is a vector quantity. Clear? So in vector form, you have to write the direction of, sorry, the value of magnetic field in vector form. How can you write this? See this. You see, you have seen that the magnetic field is going inward to the plane. Yes or no? dB. Clear or not clear? dB is going inward. And dB is perpendicular to both the vectors, dl vector and r vector. Yes or no? Because dl vector in direction of y-axis. You can suppose it is in the direction of y-axis, right? R vector is in the direction of, somehow it is in the plane. So you can consider it in the direction of x-axis. Okay? Yes or no? Clear? Okay. Now the dB is just into the plane, inside vector, in the another plane. Okay? Perpendicular plane. I mean to say dB, the direction of dB vector in the perpendicular plane. Clear? So what is the direction of dB vector? dB vector, the direction of dB vector is perpendicular to the plane of dl vector and r vector. Right here. The direction of dB vector is in the perpendicular plane of r vector and dl vector. Yes or no? It is in the perpendicular plane of r vector and dl vector. Correct? So you can write dB vector, the direction of dB vector is in the direction of, when you know, when any vector is propagating in the direction of the plane of perpendicular of two given vectors, then the direction of the that vector which is perpendicular to both of the vectors is given by the cross product. Like see here, if this is a vector and this one is a b vector, so AB vector lying on the xy plane. Look here, this is toward x-axis and this vector is towards y-axis. So if you rotate A towards B, A cross B, then the resultant vector is pointing towards the perpendicular plane, both A and B. You see, this is perpendicular both to A and B. One second. So this is pointing towards perpendicular to both A and B, and it is equals to, it is going on Z axis. So if this quantity is, you suppose C, then you can say कि C vector is in the direction of A vector cross B vector. Clear? Yes, sir. So same here, dB, the direction of dB is parallel to R vector, sorry, dl vector cross R vector, dl vector cross R vector. The direction of dB is perpendicular to both plane containing dl vector and R vector. So the vector form of this small dB is given by, previously the dB was mu naught upon 4 pi ideal sine theta upon r square. Clear beta? dV was mu naught upon 4 pi ideal sine theta upon r square. Clear? So in vector form, dB you can write mu naught upon 4 pi ideal vector cross r vector, sorry, cross r cap, cross r cap upon r square. Yes, this would be the formula of dB vector. Why? Because dB vector is going perpendicular to the plane of ideal vector, current element vector, and this r vector. So, okay, so the vector in the direction of r vector is taken r cap. Why? R cap is a unit vector, so it will not alter the magnitude of this vector. Okay, this ideal sine theta upon r square. Yes. So as a cross b equals to mod a mod b sine theta n cap. Okay, in class 11th, you must have read this. A cross b equal to mod a mod b sine theta n cap. No, no, it is in physics, class 11th, chapter number 2, motion in plane. It was there. Okay. So ideal cross r cap equals to first vector. The magnitude of first vector become ideal, and magnitude of second vector, ideal vector, you can write is ideal second vector magnitude equals to r cap. Here it is sine theta into n cap is the perpendicular vector. So ideal vector cross r vector, sorry, r cap equals to, it will become IDL. The magnitude of r cap become 1 and sine theta. Here it is n cap, perpendicular plane. Clear? Yes. Once I again want to clarify this thing. Now see here. We have derived up to the scalar form of the this magnetic field intensity equal to mu naught upon 4 pi IDL sine theta upon r square. It is fine. I know everyone got it till here and very much comfortable. Okay, because mu naught dB equal to mu naught upon 4 pi IDL sine theta upon r square. Now problem is to write it in vector form. Okay, so if you place a vector dB here, then mu naught upon 4 pi ideal sine theta upon r square dot n cap. Why it is n cap? Because the direction of magnetic field is considered as n cap. This is length current element vector dl. This is our radius vector. Okay, joining the current element to the point, and this is the direction of magnetic field, which is going perpendicular into the plane. So I cannot make it into the plane because our plane is different plane from the magnetic field plane. Okay, it is going inward to the plane of paper. Okay, like you penetrate your pen of paper inside your laptop screen or mobile screen. So that will be the exactly direction of this magnetic field going inward. So you consider that this is n cap. Okay, so you have written here it is equals to n cap. Fine. Now see mu naught upon 4 pi. There is ideal. Ideal is the magnitude of vector ideal. So you can write like this. And one more magnitude is equals to r cap. Why? R cap is the unit vector in the direction of r. So r cap, every unit vector having magnitude 1 sine theta n cap upon r square. Okay. Now last important line. All you know, vector product of the two vector a cross b equals to mod a mod b sine theta n cap. Okay. Now try to go backward. Yes, using this formula. So it will become mu naught upon 4 pi. See here, backward meanings reverse approach. You are going left to right, then you expand this formula AB sine theta. Okay. And if you're going by backward, then this means you again combine, yes, from end to start. Okay. From right to left. Okay. So this is vector A mod, vector B sine theta n cap. So can you write it ideal cross r cap or not? Yes, exactly. So this is the vector form of our magnetic field or Biot-Savart law. dB equals to mu naught upon 4 pi ideal cross r cap divided by r square. Okay. So this is our Biot-Savart law. Sorry, mu naught upon 4 pi ideal cross r cap upon r square. Clear? One more thing, by the rule of vector, vector a cap is equals to vector a upon mod of a. So here r cap equals to vector r upon mod of r. So just place it here. dB vector equals to mu naught upon 4 pi I dl vector. In the place of r cap, you can provide it here vector r upon mod of r. Mod of r can simply written as only r. When there is no magnitude, then itself it is considered as magnitude. So r square into r, it will become mu naught upon 4 pi I dl cross r vector whole divided by r cube. Yes, see here. Mu naught upon 4 pi ideal cross r upon r cube. Here the direction of dB is represented by right hand rule. Yes, you know, I already have taught you to find the direction of magnetic field because of a current carrying conductor. How, like this is a current element, ideal. So place your thumb in this direction and check where the lines of forces are moving. Does it moving towards your wrist? So it will be inside. And if it is moving outward, then it will be out of the plane of paper. And clear? Yes. So dV is perpendicular to the plane containing dl and r vector, and it is directed inward if point P is to the right of the current element. Yes, if the point P is towards the right of current element, then the direction will be inward to the plane of paper. And similarly, if the point P will be to the left of current element, dV will be perpendicular to the plane of paper containing dl and r, and it is directed outward. Yes, so we have till now we have calculated here the magnetic field intensity dB. So now we are going to making the master formula for all. dB magnitude is equals to mu naught upon 4 pi. In numerical, you have always inquired about dB magnitude. Okay, there is no question related to directions. Okay, so dB equal to mu naught upon 4 pi ideal sine theta upon r square. This is the scalar form of magnetic field intensity by Savart law. Now for B, you know B is equals to integration of dB. So just place the value here dB. dB equals to mu naught upon 4 pi IDL sine theta by r square. So take out mu naught upon 4 pi. Take in mu naught upon 4 pi outside. So it will become mu naught upon 4 pi integration IDL sine theta upon r square. Clear? Done. So this is complete about Biot-Savart law, and in this way you can calculate the magnetic field intensity due to a current carrying conductor at any point. Done. So student, we have developed here the formula for magnetic field intensity B equals to ideal sine theta upon r square. Now important features of Biot-Savart law. First, the direction of dB is perpendicular to both ideal vector and r vector. Yes. So direction of magnetic field is always perpendicular to ideal vector and r vector. So make it a very important result. Write it. What to write? dB vector is perpendicular to current element ideal. And second, dB vector, dB means B also, is perpendicular to the r vector. Clear? Yes, first thing. Second, if theta equal to 0 degree. Yes, means when your point is lying on the wire, See here, this is your wire, and this is your current element. DL, IDL is the current element, and this is your radial vector, point vector, position vector of point P with respect, and this is angle theta. Okay. So, dB is proportional to sine theta, and sine theta having its maximum value when theta equals to 90 degree, because sine 90 equal to 1. Clear? Sine 90 is equals to 1. That is the maximum value of sine theta. It means your magnetic field will be maximum when your current element is just perpendicular to the position vector of this point vector. Okay. When there is an angle of 90 degree, your magnetic field will be maximum. Clear, beta? Because the value of theta is equals to 90 degree and sine 90 having its maximum value. But in case you taken your observation point, like your previously, this is your current element, my dear, ideal. Now, if first your angle was here, theta, now you continuously decreasing, 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 and in a situation, your point comes just on your wire. Yes, here, your point is P. Now tell me what is the angle here of dl vector with r vector. Now tell me, if your point comes here, so what is the angle here? Theta is equals to how much? 0 degree. Previously it were 90, then it is continuously decreasing. Now angles come to the 0 degree. Then dB equals to what? I dl sine theta means sine 0 upon r square. My dear, sine 0 equal to 0. Yes or no? So if we place 0, then the intensity equals to 0. So very important fact is here, कि the intensity on the line, that is the point P, lies on the axis of the linear conductor. If the point P lies on the axis of linear conductor carrying current, then intensity of magnetic field equal to 0. Clear? Clear, clear? Yes. So dB equals to mu naught upon ideal mu naught upon 4 pi ideal sine 0 upon r square it equal to 0. It means there is no magnetic field at any point on the thin linear current carrying conductor. It means if you having any thin linear magnetic current carrying conductor, if anyone asks what is the magnetic field inside this conductor, your answer should be equal to 0. Okay. Yes, if theta equal to 90 degree, I told you the current element is just perpendicular to the position vector of P. Okay, so which is maximum? Yes, it is equals to mu naught ideal, mu naught upon 4 pi ideal upon r square. Why? Because sine theta equals to 1. Okay, I can derive here dB, as you know, dB equals to mu naught upon 4 pi ideal sine theta upon r square. So theta, for theta is equals to 90 degree. For theta is equals to 90 degree. Sine 90 equals to 1. So it is equals to mu naught upon 4 pi IDL sine 90 degree upon r square. Okay. So sine 90 equals to 1. So it will become mu naught upon 4 pi IDL into 1 upon r square. That is equals to mu naught upon 4 pi IDL by r square. Then yes, ideal upon r square. For theta is equal to 0 degree or 180 degree, dB equal to 0. Why? Because for theta equal to 0 degree, sine theta is equals to 0. And for 180 degree, sine theta is also equal to 0. So field will be 0. Clear? So students, we have calculated first Biot-Savart law. Biot-Savart law is completed. Now we start its application to current carrying circular loop. Yes. So first derivation to find the magnetic field intensity at current carrying circular loop. Yes. Magnetic field intensity at a point at center due to a current carrying circular loop. Clear, beta? So we're going to find magnetic field intensity at a center due to a current carrying circular loop. See here. Guys, we have developed Biot-Savart law. Okay. And the application of Biot-Savart law is to calculate the magnetic field intensity due to various current geometries. Okay, there may be straight current carrying conductor. We have to find the straight carrying the magnetic field due to straight carrying conductor. We have a circular current coil, and we have to find the magnetic field at the center of the loop. We have a circular coil. We have a circular coil, and to find the magnetic field intensity at any point because of this circular coil. So one by one, we're going to derive these relations for different type of circular loop or straight carrying loop or another type of. There may be solenoid also to find the magnetic field intensity in the case and because of solenoid. So first we are going to find the magnetic field intensity at the center intensity at a center due to a current carrying circular loop. Let us start. So, okay, start with the derivation. Magnetic field at the center of a circular loop carrying current. Make it heading. Magnetic field at center of a circular loop carrying current. So now we have a circular loop and we need to find the magnetic field intensity at the center of this loop. Okay. So consider a circular loop and there is a current anti-clockwise direction. Take a current in anti-clockwise direction flowing through it like this. Clear? Okay. Now consider a very small differential length dl on this loop. Very small length dl. Okay. This is the very small dl length. You can take it any side. Either you can take it this direction also. You see, this is dl vector ideal. So you have considered a current element ideal, right? And you have to find the intensity at the center. So this is your r vector and this is your angle theta. Everyone knows this r vector is along to the direction of radius and this angle is equals to 90°. Yes or no? The angle between any part of the circle with the radius equals to 90°. Clear or not clear? Yes. So consider a circular current carrying loop carrying current I. We have to find the magnetic field at the center of this loop. Consider a small current element dl. This should be dl on the circumference of this loop. Clearly the angle between dl and r vector is equals to 90°. Yes or no? Now, place the formula. By the Biot-Savart law, we know dB equal to mu naught upon 4 pi ideal sine theta upon r square. Remember what is the dl? Sorry, theta. What is theta? Theta is the angle between dl vector and r vector. You know? So it is equals to 90°. So sine theta is equals to 90°, sine 90 upon r square. So it will become mu naught upon 4 pi. Sine, the value of sine 90 equal to 1. So it is equals to dB equal to mu naught upon 4 pi ideal upon r square. Clear? Integrating both the side. As we have dB is the magnetic field intensity due to this small differential length. But we need to find the intensity because of this whole wire arrangement, this whole current loop. So we need to integrate it. Integrating both the side, we will get dB integration equal to mu naught upon 4 pi ideal upon r square. Clear? The integration of dB equals to b. The integration of dB equals to b. And I upon r square, mu naught upon 4 pi is a constant. I upon r square is a constant. And dl is only the variable here. What is means dl. Dl mean total length. You're integrating about the total length of the circle. And if you're having the radius r, then the total length of the circle would be its periphery or perimeter. And the perimeter, or you can say circumference of the circle, equals to 2 pi r. Clear or not? So it is equals to 2 pi r. Now cancel 1 r at the numerator by the denominator 1, and 2 pi, pi to pi is cancel, and 2 2s are 4. So your answer for the magnetic field B equals to mu naught I upon 2r. Clear? So this is the first derivation for the magnetic field intensity at the center of the circular loop carrying current. Note it. So guys, our next derivation is magnetic field on the axis of a circular current loop. Uh, we have to find the magnetic field on the axis. Just now we have find that magnetic field at the center of the loop. But now we have a loop and we have to find the magnetic field at the center on the axis of the loop like this. First, try to understand this diagram. This is our loop, circular loop, and it is placed in perpendicular plane. You're perpendicular to the screen. Like this is your plane of screen. Okay. So like this is a clock. This is 12 o'clock and this is 3 and here it is 6. Here it is 9. Now this is symmetrical axis. If you rotate this clock and somehow this clock will be here. So this is 12, this is 9, this is 16, this is 3. Okay. So this is the front view. Your clock is just front face towards you, and this is the 3D view. Okay, your clock is not perpendicular, so purely in the plane. It is in 3D. Understood, Nitin, what I want to say? Yes. Here, if you talk about the axis of this clock, so your axis will be lying here in a space. But now your clock is in a space, so your axis will be lying here in your plane. So what we have to do, there is a current carrying conductor, current I is flowing through this circular wire, and we need to find the amount, the intensity of magnetic field at some point P on the axis of this loop. Okay, on the axis of this loop, suppose the radius of wire B is small a. This is the radius of the wire. And from the center, the point is x distance away from the center of the loop, this point P, at which we have to find the magnetic field intensity. Is it clear, guys? Okay. So let us proceed here. So derivation is magnetic field intensity, magnetic field on the axis of the circular current loop. So this is the diagram. First, this one is our diagram. Clear? This is the front face and this is the backward face. Okay. Now, consider a circular coil of radius small a. So the radius of the coil is equals to a small a here. Remember, with center O carrying a current I. So the coil having the current I. Suppose P is any point on the axis of the circular coil at a distance x from center O. So OP is the x distance from a point x from its center. You consider a point P where we have to find the magnetic field intensity. Okay. So this is the point of investigation where we have to find the magnetic field intensity due to this circular coil, circular current coil. Now we consider two small element of coil, each of length dl. Yes. See here, you consider two length element. Okay. One here, this is very small, very small elemental length dl. Okay, so dl is here, very small length. Now consider two small element of the coil, each of length dl at C and D. So you have considered two length elements are here, at one at point C and another at point D, which are situated diametrically opposite edges and which are situated diametrically opposite edges. Clear, beta? Okay. Now, so if our length is real, make a vector R here. So directly join the point of investigation with this current element. Definitely, and this also join this too. Okay. What about this angle? You know, this is like a tangent, and towards every point on the circle, the tangent is making an angle of 90 degree. So this one angle with the loop is equals to 90 degree. Clear or not clear? Yes. This distance is x. This distance is how much? X. Clear? So consider both the angles are working as taken as phi. Why we taken this angle as phi? Because theta we have reserved for the angle between dl and r vector. Theta is the angle between dl and r. Yes or no? Yes. In the derivation, we have considered theta is the angle between dl and r. You see here, theta is the angle between dl vector and r vector. And here theta becomes how much? 90 degree. Because the tangent is just perpendicular. So here theta is equals to 90 degree, right? So we have considered another angle phi. So both the angles should be equal as the diagram is symmetric. So this is equal to phi. Now if this is x and this radius is a, then Pythagoras theorem, you must write r square equals to x square plus a square. Clear, guys? So r equals to under root a square plus x square. Okay. So r equals to under root x square plus a square. And both the angle CPO equal to DPO equal to phi. So both the angle considered, let CPO equal to DPO equal to phi. Okay. According to the Biot-Savart law, now according to the Biot-Savart law, magnetic field at point P. Now we have to find the magnetic field at point P due to this current element. Okay. So magnetic field due to point P, due to current element ideal at C is given by, yes, it is not C, it should be P. Okay. Because our investigatory point is P. So magnetic field is given by how much? Wait. At point C, it is equals to, yes, sorry, it should be C. No problem there. It is only C. First, we have to find the magnetic field because of this point. Yes. So formula equal to, because of this current element, there is a current element. So there is a current element like this. So because of this point, magnetic field dB is given by, look here, dB is equals to mu naught upon 4 pi I dl sine theta. And as I said here, theta is equals to 90 degree. So place here the value of theta is equals to 90 here. dB equals to I dl sine theta upon r square. So theta is equals to 90 degree and sine 90 equals to 1. Right? So this is equals to mu naught upon 4 pi I dl upon r square. My dear, what is r? R equals to under root a square plus x square. So r square equals to under root a square plus x square. Again a square. A square and root will cancel out. And here it will be only a square plus x square. Clear? So this is the magnetic field because of this point C. Okay? Yes. According to magnetic field, Biot-Savart law, the magnetic field at point P because of um, due to the current element at C is given by. So this is the magnetic field dB at point P. But because of this segment C, this element C, this is the magnetic field because of point P. Clear, beta? Now, this is dB. Similarly, there is also one more magnetic field of the same intensity because of diametrically opposite current element of length dl. Again, it is equals to dB. Okay, the same magnetic field will be dV, will rise here because of this current element at D. Clear, Nitin? Okay. Now, very most important concept here. You see here, this vector R having an angle phi with the axis. Okay, with x-axis, with x-axis. Then the magnetic field dB, you know the magnetic field is exactly perpendicular to the position vector. So it will be oriented towards here, which is an angle 90 degree. Wait, I make you understand. See here. Like this is vector R. Clear, beta? And you know, vector R and dB vector are always perpendicular. Why? As I have written, you see here, during the derivation, I told you vector R and vector dB are always perpendicular. dB and vector R are always perpendicular. Here it is. Hmm, wait. Yes, this is the concept here, that the direction of dB vector is perpendicular to both ideal vector and R vector. So dB vector is perpendicular to ideal current element and dB vector is perpendicular to R vector. So using this concept here, so dB vector is perpendicular to the R vector. So this is R vector, then dB vector should be here. Okay, beta. Now, if R vector is like this, yes, R vector is like this. If I rotate at an angle phi, then previously your vector was, dB vector was here. But if this rotated by angle phi, then your dB vector should lying here. This also should have to rotate with angle phi. Say yes or no. See, like this is a plane L, geometry L. Yes. So if you rotate L this side and this you angle given to this branch as angle phi, then this branch is also moved with an angle phi. Okay. So this one, the previous L with the white color, and this is your new L with the green color. Understood? When you moved one branch with angle phi, then its one arm also lifted up with angle phi. Same concept takes place here. See here in this diagram. If this is angle phi, vector R making an angle phi with the x-axis, then perpendicular to the vector R, that is dB vector, will make the same angle phi with the y-axis. Clear or not clear? It will make the same angle phi with the y-axis. Similarly, here, if this dB vector makes an angle, sorry, R vector makes an angle phi, then here the dB vector will be exactly perpendicular to the R vector. Look here, this is exactly perpendicular to the R vector, but it will make an angle phi with the y-axis. Okay? Why? Because you consider previously your L is looking like that. This is your plane L. Now you tilt this edge by an angle phi. So you have tilted this edge by an angle phi. Then this edge will also become tilted with angle phi. Yes or no? Understood. See here, this angle phi is here. This one angle is phi. So this is also lifted up with the angle phi. Clear? So the both the angles are phi. Done? Okay, so now resolute the components here. What we have vector B here. So this is dB and this is angle phi. So in the direction of phi, there will be a resolution of component that is equal to dB cos phi. Again here it is equals to dB cos phi in the direction of phi. So here it is also dB cos phi. Now resoluting this component, the above one component will break into dB sin phi and the second one component give its horizontal component as dB dash sin phi. We have considered the another one intensity because of point D is dB dash, but numerically dB is equals to dB dash. Magnitude wise, dB equal to dB dash. Okay, because the distances are same. The above R and the lower R will be same. Now dB cos phi and dB cos phi will cancel each other, and the resultant intensity is because of both the sine component. So see here, the direction of the dB is in the plane perpendicular to DL and R, and it is directed as given by right hand screw rule acting PE perpendicular to CP. Similarly, the magnitude of the magnetic field at P current element of length DL at D is given by, means the another magnitude will be same, dB equal to mu naught upon 4 pi sine theta upon r square, so ideal upon mu naught upon 4 pi ideal upon a square plus x square. It simply means both the magnitude because of this segment and this segment will be equal in magnitude. So dB equal to dB dash. Now this is a line since the component of the magnetic fields along the py and py dash are equal and opposite. I am talking about the upper one component, so they will cancel in each other. So they will cancel each other and the component acting along the px in the same direction will be added up. The same rule is true for all the diametrically opposite current element of the circular coil. So the total magnetic field at the point P due to the current through the whole circular is given by, look here, students, dB as we got dB, the working element dB as dB sin phi. Okay, the component here is equals to dB sin phi. Now total field, magnetic field B is the integration of dB sin phi over the closed loop. Why? Because you see the net component that working here is dB sin phi, right? So integrate the dB sin phi over the closed loop. So dB sin phi integration dB sin phi. Place the value of dB mu naught upon 4 pi ideal upon a square plus x square. This is the value of dB, and now here it is sin phi. You know sin theta is equal to perpendicular upon hypotenuse. So what is perpendicular? A. What is hypotenuse? Under root a square plus x square. Look here in the diagram. This is angle phi. So sin phi is equals to perpendicular becomes a and hypotenuse becomes r. R means under root a square plus x square. So sin phi is equals to a upon under root r square plus x square. Clear? So place the value of r square plus x square, a upon under root r square plus x square. Yes, sin phi. So mu naught into I, constant outside, mu naught upon 4 pi, a square plus x square. Sin phi is also constant. Inside the integration, it is dl. And what is dl? dl is the total length of the loop, that is equal to 2 pi r. But in the place of radius, we have a, so it becomes 2 pi a. So place all the value and you have final derivation mu naught I a means a ka square into 2 pi below 4 pi a square plus x square and under root a square plus x square. See, a square plus x square having full power considered as 1 and a square plus x square having half of the power considered as 1 by 2. So it is equal to a square plus x square whole to the power 3 by 2. 1 plus 1 by 2 becomes 3 by 2, and this intensity will along px. So final derivation b equal to mu naught upon 4 pi 2 pi a square I a square plus x square whole to the power 3 by 2. If n turns are there, your field will be n times. Just take 2 pi n. Clear? So this is complete derivation for this axial on the position of axis. Okay. If you want to find the intensity at the center of the loop, okay, you have find the intensity at distance x, but for the center, x will equal to 0. So place if x equal to 0, so you will have x equal to 0, b equal to mu naught upon 4 pi, 2 pi nia square upon a cube. 2a will cancel the 2a and only the answer mu naught upon 4 pi 2 pi ni upon a, that is equals to mu naught ni by 2a. Same result we have obtained here. See here, just before we have done this derivation, mu naught I upon 2r. So for n tons, b equal to mu naught ni upon 2r. Same we obtaining here. Yes, see, mu naught ni upon 2a. Here radius is a, there radius is r. Clear? Yes. Okay. So guys, if I talk about direction, so direction of the magnetic field is oriented about positive x-axis. So that is equals to I cap. So for writing vector notation, you should have to write here I cap. Okay. So if you're writing a vector notation of this one, then B vector here and place here, it is a I cap. As the direction is towards the x-axis, the resultant direction is toward x-axis. Clear? Okay, student. So we have the derivation mu naught upon 4 pi 2 pi I 2 pi n I a square upon a square plus x square to the power 3 by 2. Now one special case is if x is very very greater than a, if point is very far away from the center, then b equals to mu naught upon 4 pi. If x is very very greater than a, then a square plus x square. So it is approximated as only x square, because radius should be radius can be considered as very small. So mu naught upon 4 pi 2 pi n I a square upon, now a square plus x square become what? X square whole to the power 3 by 2. Now 2 से 2 cancel, 2 and 2 cancel, and pi to pi cancel, 2 to 2 cancel. So your final result equals to mu naught upon 2 I a square n divided by x cube. Yes. So this is the result, a special case you can see. So this, see here, mu naught I upon 2x cube. Clear? Mu naught I upon 2x cube. If a is negligible, yes. So we have to neglect a also in the numerator also, numerator too. So if you neglect a square in the numerator, it will become mu naught I n for n terms upon 2x cube, having the same result. Clear?